So I'm going to give you a quick, literally whistle-stop tour of NoSQL and MongoDB in particular, and then we're going to go straight into looking at some code and how we do basic stuff like CRUD operations, and if we have time at the end, then I will show you a slightly more sophisticated piece of code which shows you some of the more advanced capabilities of MongoDB, like transactions and change streams. Think of it as reactive programming environment. The key thing about PyMongo is it's an incredibly natural model for programming with MongoDB. Because MongoDB is effectively a JSON database, the objects that you manipulate via the PyMongo driver are effectively Python objects, dicts, arrays, strings, integers, the whole 9 yards. So it's a very natural programming model for anybody who's coming from the Python community. Safe harbor statement, we're a public company. If I make some future-looking statements, the main commitment is that they may or may not be delivered in the future, where the future also includes the heat death of the universe. So, don't build your whole strategy around anything I talk about today that's future-looking. I want to give you a quick overview of 4 types of NoSQL databases: key value stores, wide column stores, graph stores, and document stores. MongoDB is a document store, but I think understanding how these others work allows you to position MongoDB and lets you understand where and when it might be appropriate for you to use. So think of key value stores, they're just associative arrays. If any of you use Memcache is an associative array that puts a caching layer on top of MySQL. They're very fast. They typically use a hashed lookup. Think of it like a dict, but with a backing store. And they're great for looking up single key values, just the way a dict is. But if you want to query on the value type, if, for instance, you wanted to look at a basket by the value of the items in the basket, i.e., I want to find all baskets with over $100 worth of value. If you're using a key value store, then you have to table scan because the values aren't indexed, just the keys are indexed. So you have to basically look at every entry, and that can get tiresome if you've got millions of entries. Even on fast computers, scanning millions of rows takes a long time. So key value store is great. I mean, the ones you might be aware of are Couchbase and DynamoDB. Now, both of these have added more sophisticated querying models in the past, but at their core, they're a key value store. And then you've got the more traditional database stores, and most relational databases you'll deal with, MySQL, SQL Server, DB2, are row stores. And that means we align the rows in order, and they're stored, and the rows are fixed length, right? That means it's very fast to find a particular row if you know where that row is. And an index is typically a way to tell you where a particular row is, so you can get most rows with a single seek or maybe a couple of seeks through the B-tree index. And they're stored in order. And this storing in order creates problems for relational databases in that if you want to add a column, you effectively have to rewrite the whole database because you have to make space for that extra column. So if I wanted to add an end date to this, I'd have to take the yellow block, take it out and append the end date value, and then do the same for the green and same for the purple. And again, if you're trying to rewrite your whole database, if you've got 100 terabytes of data, that can take a very long time. This is what we mean by inflexible schema in relational databases, and anybody who's ever had to do an alter table in a relational database knows what a pain in the hoop that is. Wide column stores do something slightly different, and the kind of wide column store you'd probably most be familiar with is Cassandra. Wide column stores store the data in column order. And why do they do this? Well, because often I want to do something with a single column. And for analytical processing, I might just want to know what the total salaries are for the company. So I want to read just the salary column. Or I want to analyze the start dates and find out which people started on or after a particular date. Well, a wide column store takes the table and kind of pivots it and stores the items in row order. And this has 2 benefits. One, you're not reading the whole row. Typically, when you iterate through a relational database looking for just one column, you have to read the whole row to get that column entry. Well, with a wide column store, you just read the column you need. And you get excellent performance in terms of compression because you're compressing the same type of data. And so typically wide column stores do really well on compression, and so your read fan out becomes much less. So wide column stores, Cassandra, great. Brilliant for when you want to just look at the columns. Again, if you want to look at the whole row, not so hot, because look what they have to do. They have to seek to the one element, then they seek to Joe D, then they seek to $2,400, $24,000, then they seek to start date. So you get a lot more seeks. And lots of the more sophisticated database engines will store data in both formats to make things more efficient for you. But that has its own problems in terms of write synchronization. Graph stores, great for graphs, pretty sucky for everything else you might want to do. Walking a graph is great, but most people want tabular access as well. The Neo4j is probably the most popular graph store. Almost everybody who runs a graph store runs it alongside another data store, right? Because graph stores, once you've done your graph querying, there's all the other queries you want to do that graph stores don't support. And then document stores. This is what MongoDB is, JSON documents. And the reason we differ from, say, a key value store is within this document, we can index at any level in the document. So you could index error codes, you could index expertise, and we would automatically index into the array. You could index location, and we'll give you a geospatial index. So you get a much richer structure. And because this is JSON at the core, you can change the object structure with each new insert, and that gives you wonderful flexibility. As you change your use case, as you increase your business footprint, you can add new fields to your data with no downtime from the database. And it's typed, right? JSON is not typed, but within MongoDB, we encode the JSON in a binary format called BSON, so we know that these are strings, we know their length, we know the sub-object address is a nested document. We know that expertise is an array. We know that location is a geospatial index. And by adding this type field, we make it very efficient for shipping these documents across the wire, and of course for storing them in the database and retrieving them. If you've ever used protocol buffers, it's a very similar approach. But from your perspective as a programmer, it's just dicts, arrays, and tuples. We do all the heavy lifting of converting the objects into BSON for distribution on the wire and pulling that data back out and converting it back into your Python objects. This is what makes it such a natural model for programmers. And, you know, we understand JSON, so we can create indexes. I've kind of talked about all of this. And it's a binary format. Here's the binary encoding of JSON hello world. We've got a total document size encoded. Then we've got a type string, which is 2 for strings. Then we've got the field name, which is hello, and it's null terminated. Then we've got the field value, which is size, value, value, and null terminator, and then an end of object. So this is what you would look like if you looked at the object on the wire. We have a complete spec for all the mappings of all the objects. Every driver in MongoDB effectively encodes its data to BSON. So you could use Java and you'd get the same object as you did in Python. This makes it very attractive for people who want to use multiple programming models but have the same standardized data format on disk and in your database. So we can manipulate the same objects with Python, with Java, with Ruby, with C Sharp, and it all happens in terms of BSON specifications. And we're not that radically a departure apart from being JSON at the core. You know, we have databases, relational databases have databases. Relational have tables, we have collections. We call them collections because they're not fixed format, they're storing JSON objects. We have parent-child tables, we call them nested subdocuments or arrays. We both have indexes. Relational databases have rows, we have documents. Relational databases have columns where we have field names. Relational databases have joins, we have $lookup, which is effectively a join operation that you can apply. We both have views, and now recently from 4.0, which was launched a year ago, we have multi-document transactions. And that means you can effectively update multiple collections within a begin and a commit transaction and give yourselves all the ACID guarantees that we know and love and desire from our relational databases. So we like to think of MongoDB as the most relational, non-relational database. Apart from the query language, which uses JSON, you should see exact parallels with everything you've done in MongoDB or in MySQL or your own favorite relational database. But it's a distributed database. So we run multiple nodes in parallel. And the most trivial kind of replica set you can create is a 3-node database. We have one primary that takes all the write operations, and then we have 2 secondaries that will effectively take duplicates of the data. And so when we set this replica set up, and I'll show you how to do this in a minute on our database as a service, we create this replica set for you. They define the connections between them. They give you heartbeats between the 3 different nodes. Writes go to the primary and are replicated automatically to the 2 secondaries. Guaranteed that if you read and write from the primary, you'll always get strongly consistent data. You can read your own writes and guarantee that you get them back. You can choose to read from a secondary and you will end up with eventual consistency because clearly there's some latency between writing to the primary and replicating to the secondaries, especially if the primary is in Dublin and the secondary is in New York. There's natural latency over the wide area network. And so this is normal operation. Heartbeat tells us everything's going, everything's working fine. We're writing to the primary. Suddenly the primary dies. Imagine we shoot the primary, somebody clips a cable, the disk runs out of disk space. Well, straight away, within election timeout millis, which is generally about 500 milliseconds, the 2 secondaries will detect that there's no primary, right? And you can tune the election timeout millis depending on the set scale of your network and the distance between the nodes. And so they're going to have an election. And they're going to have an election to create a new primary. Without a primary, any writes that the clients attempt to make will be held by the driver. And if there's a write in flight at the time that the primary goes down, we'll retry that write when the primary comes back up. If the primary doesn't come up in 30 seconds, then we'll generate a server timeout on your client application, and then you've got to deal with that. That's effectively your database is down, right? But the whole point of a replica set is that you should have no single point of failure. So when we build these replica sets in Amazon, in our database as a service called Atlas, we effectively split them across multiple regions. And so we're isolated in every way. So the 2 nodes that are remaining we need to have an election. They have an election and they elect node 2 as the primary. Effectively, they'll look at the node that has the most recent up-to-date data. And then they carry on as before. Now, clients who are trying to connect will reconnect to the primary, and then writes will continue as before with no interruption of service. What you'll see from the client side is a short delay as writes are held at the driver or as a write is retried. And now everything's as before. And while this is a failure, we can also use this ability for preventive maintenance, where we can rotate nodes out of the cluster to upgrade their operating systems, to upgrade MongoDB, to change the disk parameters, et cetera, et cetera. So now everything's working, but now we want to return node 3 to operation. So we go down to the data center, we discover somebody pulled a cable out, we plug that cable back in, and now node 3 is going to wake up and it's going to go, I'm back, what did I miss? They'll ask the primary, and the primary will go, well, here's what you missed since you were dropped out of the cluster, and there'll be a synchronization period. And it takes, depending on how long the node has been down and how much data gets written, it might take a couple of minutes, it might take a couple of hours, but eventually that node will catch up to node 2, and now we're back to normal operation. We don't move the primary back. The primary can sit on any node, and that's why we ask for when you're configuring these replica sets, you give them identical configurations. You could force the node 2 to come back by setting a priority value, but really it's absolutely comfortable for that primary to move around the nodes. The drivers are designed to connect to any node and use that node to find where the primary is. So you don't need to know the total topology of your network. You just need to know 1 or 2 nodes' IP addresses or DNSs. Once you connect to them, they'll inquire of the total topology, and when they've done that, they'll return and start writing again.
So when you're trying to sync stuff from the primary to the secondary, and the primary dies at that point in time, so the secondary completely synced. So is there something that you guys deal with that as well?
So if the primary dies during synchronization, then you would have a problem, right? In this particular topology, because you'd have one node that wasn't synchronized and therefore not a full member. The other node is not a full, is only a single member, and you no longer have a majority of votes to allow it to elect a new primary. At that point, you'd have to take action. It's, you increase the risk of failure when you lose parts of your cluster. So a 3-node is our default. You could make it a 5-node, a 7-node. We recommend we use an uneven number of nodes. That way, if you get a network partition, at least half the cluster will have enough votes to bring up a readable quorum. But yeah, if that happens, then yeah, you're going to be out of luck. Then you need to go and do some manual resets. So imagine you lose node 3, like there's a data center fire and that node's gone. Obviously, synchronization will take longer in that situation. In that situation, you can take a dump of the disk on node 2 and put it in place, and then catching up doesn't take as long. So it effectively speeds up the synchronization. But if you want absolute guaranteed fault tolerance in the face of single and second node failures, you run a 5-node cluster. And you can increase the number of clusters. You have up to 50 nodes in a replica set, right? So we have a couple of our largest customers will run a replica set which has a node in every data center that they run. And that way, you could lose 20 nodes and you'd still have a viable replica set that you could write to. But that's pretty unusual. You wouldn't, you really want to have some kind of catastrophic failure. Typically, those kind of failures originate from your code or our code having a catastrophic failure. But in the lifetime of my time at MongoDB, I've been here 6 years, I've never seen a replica set have catastrophic failure where over 50% of the nodes failed at the same time, unless there's synchronization at some other level. So what you see is people running a replica set on top of a virtual machine or a collection of virtual machines, and those virtual machines, unbeknownst to them, are all running on the same physical hardware. The hardware dies, your whole replica set goes up in smoke. Don't do that. We guarantee that won't happen with replica sets configured by ourselves in Atlas. I'm going to zip through sharding really quickly because we're short of time here and I want to get into the code. Sharding is just a way to scale out a single replica set. If you imagine a replica set has a single node you can write to, it's easy to saturate that node, while a sharded cluster is effectively multiple replica sets running in parallel. So I'll give you the big picture. So you can imagine you've got several replica sets. We run a separate daemon called MongoS that does the routing from your application to the specific shards. And because you can run as many of these shards as you want, you get n primaries. That's n nodes to which you can distribute your writes to. And of course, n nodes which have n memory footprints that you can host and cache your data in. And we configure all this with a config server. So everybody here can sign up for the MongoDB cloud. This is the best and easiest way to set up your MongoDB clusters. It's free. You can set it up today. You go to the MongoDB cloud, you set up your free cluster. It's free forever. Every individual in the room can do this like today or at your leisure. You can also, at a discount code, JD100, which will give you $100 worth of credit, and that will allow you to set up. And putting in the discount code is actually a little funky. So I'm going to show you how to do that now. So you'll see, come on, don't die on me now. So over here, it will always start you at a project level, but you want to go up to the top level, which is the organization level. And this will refresh. And then there's a billing tab, and it's on the billing tab that you put in the discount code. So over here, we'll go billing, and you scroll down here. Scroll, not move. And see there, buried in the middle of the page, apply credit. That's where you put in JD100. I'm not allowed to use my own codes on my own environment, but that will give you $100 worth of credit. And if anybody wants credit after that, you can just shoot me a direct message on Twitter on Joe Drumgoole. I'm very happy to share credits with people. You will have to put in a credit card to do this, so it's not for everybody's case, but if you don't want to do that, you can just build a cluster. If I go back to my projects level. So if you go build a new cluster, you can pick AWS, and you'll see that little blue chevron, free tier available in Ireland. And I'll go down, and it defaults to M0, so it's free tier, so I'll just change that to be free tier, and I'll create the cluster. And it'll just go off and do that cluster. No credit card required. Now, don't run your production systems in that cluster. It's a shared cluster. It's probably good for a couple of users, maybe 10 users, but your performance is, it's going to be very variable. But you can use it forever, no problem. Now, back to code. So JD100 gets you $100. And you can build that cluster. There's also a sample data set you can load, which gives you some data to play around with. You can just pick that off that little ... there. And then we can connect to it via the Mongo shell. And when we do that, we're going to get this server here. So I can show you connecting to the shell. Let me just pop up. How's that look? Can we read that? Can I just bump that up a bit more? And so there you can do show databases. Gives you all the databases, and I can say use blog. And I can do show collections. And there's articles and users. Now you can also see the same data on your cluster. If I go down here and just get the clusters up. This is the cluster I've connected to. And so if I want to make data on this cluster, I can just use the shell here. But actually for Python programmers, I think it's easier if we use the Python shell. So now I can do import PyMongo. And now I can connect. So I'm going to just get a little so host equals OS. So I have a host set up here. So there's a little password in there for you that are fast. And now I can do client, if I can type it. And I can just put in host. And you can see the client object there is connected to this cluster, PyCon IE shard, blah, blah, blah. And you can see there's a bunch of other information there. And now I can make a database. So client is, and we'll call this PyCon IE. And if we look at the database, that's a database object there. You can see the name here is pycon.ie. And now I'm going to make a collection. And that is going to be data. And if you go over here, we can see, I'll just do a refresh here. got to get the right database. Where's my database gone? Okay, we'll carry on. And now I've got a collection. I can now insert a document. And we can just call this name. And notice how I'm just creating a dictionary here on the fly. And we get an insert one result. And I can now find that particular person. So we just do find one. And there we go, that's me inserted. So now you've made your first document in MongoDB. It's that easy, and it all can be done inside the Python shell. So you can do a lot of interactive playing around inside the shell. And we have a Mongo shell that uses JavaScript, and sometimes it's better in JavaScript, sometimes it's better in the Python shell. I find the Python shell much more engaging to use. Yes, sometimes the results need to be turned into objects, but it's pretty fun. So you saw that what I was doing there, inserting your first record. We create a database. Note that you don't have to do any DDL, right? You just you name the thing and it springs to life. So you name a database, it springs to life. You name a collection, it springs to life. You name a document, it springs to life. It's very easy to get up and running. We like to think it takes less time to put a document into the database than it does to download it. And you'll see that every object gets its own primary key, right? We add this automatically. It's created on the client, so there's no round trip to the server. And it's split into 3 sections. There's a timestamp, so you get a temporal order on your inserts. There's random value, guarantees that it's unique. And then there's a count, and that count is again started as some random increment. And this is always an indexed field. So every document that you insert, and so if I go back to my Python program, I can go back and do another insert. And if I do a find now, rather than a find one, to get all versions of the document, I've got to do a little bit of messing around. X.next. There's the first one, and there's the second one. It's the same document, but the uniqueness is coming from the object ID, which is generated automatically for every inserted document. And that underscore ID is guaranteed to be a primary key, guaranteed to be unique. If you try and insert this, if I do collection.insert one, and I cut and paste this in so I effectively include the ID. Sorry, what have I done there? Oh yeah, I need to include the object ID as a type, and I'm not going to do that because it'll take too long. But effectively, if you try to insert that object, you would get an error because the object ID is already in use. So imagine I did collection.insert one. And I can override the ID to put my own ID in, so I could call it one, and name is JD. Now, if I do that again, you're going to get an index error, right? But it means that you can create your own underscore ID if you choose to. So if you're loading a database system in which you know there's a unique ID, you can use the underscore ID field rather than having it generate an object ID for you. And you save yourself an index. Because if you're creating that field yourself, it's going to be unindexed by default. So you can use the underscore ID to effectively supplant the default object ID and give yourself a free index. But you must have unique fields. If you try and insert the same object twice, you'll get a duplicate key error. Not going to show comments. So let's look at a simple blog application. Let's create a blogging application with articles, users, and comments. You do a typical entity relationship diagram with this if you're doing relational. But with MongoDB, you can just get started and work along organically. So we use blog, and we switch to the DB blog. Then we insert the first user with a password and a lang. We get a right result, and we find one, and there we have it. First user. We've created a user collection straight away. That's the first thing we need in our new blog application. How do we do this in a program? Well, with PyMongo, we create the client, as I showed before. We create the blog database, which springs to life automatically. We create the users collection, and then we just insert one, right? And we just put the same document in as before. And then when we find and print that user, we'll get the user we had before. Really straightforward, like 5 or 6 lines of code, right? Now we want to build articles, right? So articles are a little bit more complicated. We're going to create a new articles collection. We're going to have an author, which is Drumgoole, which is effectively a reference to the users collection. And then we're going to create an article, and it's got a title and a body and an author field. And notice we're using the author name, and then we're using a set of tags. And now we're going to check, we're going to do our own referential integrity. We're going to find one, make sure that the author exists in our users collection, then we're going to insert the article. Otherwise, we're going to raise a value error, author doesn't exist. This is how referential integrity is done in MongoDB. We don't use explicit foreign key references. Why? Because I guarantee you someday you're going to want to get rid of that foreign key reference, and that is a total pain in the hoop to do in relational. So we just basically use the references as references in code, gives you a lot more flexibility, especially if you're changing these documents. So now we want to create a new type of article, right? This one has a section and a post date, because we realized, oh, hang on a minute, how can it be a blog without a posting date? So now we just put in the new post date, same model as before, we just insert it and away it's going to go. It's going to work. This is a new document type. We could go back now and add that field with an update to the other inserted documents. So now we want to make a pile of articles, right? So we're going to have a make article and a make user. We use some random strings to make these. And we're going to drop the databases because we want to do this every time for demo purposes, and I want to drop this collection. If I don't drop the collection, I'm going to get duplicates, and that's going to be a problem for creating indexes later on. And now I'm going to do something different. If you do an insert one for every insert, what you're doing is you've got a round trip to the server and a response back. And what you want to do is do a much more efficient thing, which is try and upload a batch of documents at the same time. And so we use this insert many operator. So we're going to make a user and append it to the users list. And then when we get to 1,000 users and basically insert many, you can hand it a list of 1,000,000, but it will batch into 1,000 inserts a second. So we just make that split for it. And when you do this, you're literally going to 10x the performance of your inserts. So insert many is your go-to for doing lots and lots of different inserts. Typically, if you're bringing in sensor data, what you don't want to do is do an insert operation for each sensor entry. You want to batch them up into batches of 100 and stick them into the database. And then when we find a user, we're going to do ID user 1, password comma, and we're going to find that user, right? If we want to find a named user, we use the ID and the user 100, and we're going to get that person again. And now we want to find somebody with high karma, right? So with karma field inserted in the user. Well, this is how we do a kind of a range query, the kind of query I talked about before. So we're going to do db.users.find karma greater than 450. That allows us to query for a particular range. And you could have greater than or less than. There's Boolean queries and or not. So you can build quite sophisticated queries. And it makes doing querying in MongoDB almost exactly analogous to building your SQL queries. And of course, we can then use projections. So the second argument here, the karma1, lang1, says, I only want to see the karma field and the lang field. This again reduces the amount of data returned over the network to your client, so you can reduce the amount of total bandwidth consumed by each query. And now we get something that's a lot easier to read as well in the client. So we're not going to do the exercise. And now we want to do update. How do we add a comment field? Because now we realize our blog's getting some traction and people want to put feedback on. Well, we can use the update operator. So again, we're looking at ID 19, and we're going to set the comments field to be an empty array. And now what we'll see down here is we get the same document, ID 19, title is title 19, the body is random string, the author is user 1370. We've got the post state that we'd find, and now we've got an empty array for comments. How do we add a comment then? Well, we do the same update operator, and we use $push, which effectively appends an item to array, and we're appending a sub-document. So user Joe Drumgoole, comment, hey, first post. And now what you'll see is the comments array becomes an array of sub-documents. And now we can continue to add sub-documents, and they'll be in order, very straightforwardly. And then delete, again, just articles.remove, and you give it an ID or some selector string, and it will remove them. You can delete many articles, or you can delete a single article. So let's have a quick look at users again. So we do find one, we're going to get that user back, but if we ask it to do an explain, right, so find it and explain, we're going to notice something. The winning plan has a collection scan. That means we're looking at every entry. Why are we doing that? We didn't create any indexes, right? And that will work fine for collections of 100 documents or 1,000 documents, but you put 1 million users in there, things are going to get funky. So now we look at the execution stats on the explain plan, and we're going to get a much more detailed breakdown. And what we see here is, total keys examined is 0 because we've got no index. Total docs examined is 100,000, and that's a crazy amount. We've looked at every document in the collection, and that's, even 1 million is okay once you've warmed them up into memory, but if it's 10 million, you're going to have a problem. So what do? We create an index. db.articles.create index on the title field, and 1 means ascending, -1 means descending. And now you've got the index. It's just going to work. We can set a whole bunch of parameters. We can specify to create in the background. We can define it as unique. If we want to make sure that we don't have duplicate keys, we can give it a name. We can drop the index, and we can list the indexes in the shell. And so what we look for is these stages. Call scan means a collection scan. Index scan means we're using an index. Fetch and shard merge are for when you're doing queries on larger clusters with sharding. And now if we look at the stats, we'll see the total documents examined is 1, and the total keys examined is 1. And effectively, the execution time goes down to 0. And really, anything over 100 milliseconds is considered a slow query in MongoDB. In fact, we'll flag that in the log file as a warning to you. And if you're using MongoDB Atlas, you'll get emails when your users run slow queries, because we consider that to be a problem of your application. So getting that kind of notification immediately lets you know that, well, perhaps we should be adding an index on these fields. Now, that does not mean we index every field, because that creates all kinds of performance in terms of write fan out. So what have we learned? Well, we've learned how to create a database in a collection, how to insert content into that collection, how to query the collection with find, how to update a document in place, how to delete a document, how to check the efficiency of an operation with explain, how to add an index, and how to check that index is being used. That's all the tools you need to build a very sophisticated MongoDB application. I'm not going to talk about the framework. I will say all the code in this example is in Back to Basics 2018. You can see all the code there, the Mongo client, the insert, create user, create articles, many articles. You can see the many articles code in here using the exact same structure. And if you want to look at a more sophisticated MongoDB application using transactions and cursors and change streams, you can look at, where's my cluster's gone? You can look at microservices exemplar, which actually has a quite sophisticated basket management system for an e-commerce website, including the ability to take watch cursors. This is the one thing I do think you should look at. Let me see if I can bump up the font here. So you see this little bit of code here? You can watch any collection and get all the documents that are written to that collection. And that allows you to effectively do event-based programming based on changes in your collection. So for instance, here we watch the e-commerce collection and we check for documents that have more than 0 products when they're sold, and we can basically put them into a brand new collection called a snap collection. Very easy to build, very sophisticated event-based and reaction-based programming. So there you have it. MongoDB, simple to use, perfect for Python, easy to get started. Definitely want to use MongoDB Atlas to get your free cluster up and running. And when you want to build more sophisticated event-based applications, all the code is there in Microservices Exemplar. Thank you very much.